Hello everybody, my name is Mohammed Faris. I am an undergraduate student at the University of Buffalo. My major of study is electrical engineering. Currently I am a senior level. My expected date of graduation is May of 2017, and today I will be briefly cover the topic of high Kappa dielectrics. The term high K dielectric refers to a material with a high dielectric constant K as compared to silicon dioxide. High K dielectrics are used in semiconductor manufacturing processes, where they are usually used to replace a silicon dioxide gate dielectric or another dielectric layer of a device. The implementation of high K gate dielectrics is one of several strategies developed to allow further miniaturization of microelectronic components, colloquially referred to as extending Moore's law. According to Moore's law, the number of transistors in a chip will double every 2 years. As the number of transistors increase on a chip, the size of each individual transistor grows smaller while keeping the same or better amount of efficiency. As a transistor becomes smaller, however, the bounds of physical limitations become reached to a point where it can no longer get any smaller, to the point where electrons may not even pass through. In the mid-1990s, Intel came up with a solution. This can be achieved by changing the dielectric inside the transistor from silicon dioxide, which has a dielectric constant of 3.9, to something with a higher dielectric constant. Having a higher dielectric constant K provides more capacitance through the parallel plate capacitor and even increase the drive current through NMOS and PMOS transistors. Transistors can now measure into atomic levels to around 10 angstroms, but as transistors become smaller and smaller, the thickness of the silicon dioxide decreases along with it. When the gate thickness of the silicon dioxide reaches around 2 to 3 nanometers, the insulation of the silicon dioxide starts to let electrons through it, causing what is known as leakage current, leading to a higher power consumption and a less reliable drive. When the thickness of the silicon dioxide reaches 1.2 nanometers, the leakage current density can reach up to 100 nanoamps per centimeter squared, which will break most devices when connected. If we go even smaller, the surface of the oxide will cause fluctuations to the characteristics of the device. By using dielectrics with high constants, usually greater than 10, we can keep the thickness to normal conditions while increasing the capacitance. The most popular high Kappa dielectrics are the ionic transition metal oxides. Transition metal oxides are usually used on crystallized silicon, then thermally grown. To create dielectrics with the wanted electrical properties, the dielectric has to have great interfacial and bulk properties with uniformity. Multiple techniques to deposit high Kappa dielectrics on silicon can be used, such as chemical vapor deposition, plasma-enhanced chemical vapor deposition, metal organic chemical vapor deposition, atomic layer deposition, plasma-enhanced atomic layer deposition, physical vapor deposition, molecular beam epitaxy, ion beam assisted deposition, reactive sputtering, thermal vaporization, or solid gel deposition. The most popular used deposition techniques are the metal organic chemical vapor deposition and the atomic layer deposition, which can create widely known dielectrics such as aluminum oxide, zirconium dioxide, hafnium oxide, zirconium silicate, and hafnium silicate. The first problem in CMOS technology with high Kappa dielectrics started with charge trapping. Charge trapping has the ability to change the threshold voltage of a transistor over a period of time and can therefore cause major changes to a transistor's properties. The trap's levels of energy are very large and contribute to tunneling. It is caused by uneven surfaces of the dielectric when metal organic chemical vapor deposition is used. By using a single layer of atoms like atomic layer deposition, we can create single atom layers that are uniform throughout the surface. This leads to the next problem. Fermi level pinning, where powering the transistor from cutoff mode to saturation mode required more voltage than theoretically required. And once the transistor was successfully turned on, the charge carrier mobility became very low, which can slow the speed of the device. The phonons slow down the passing electrons when they pass through the metal gate and severely reduce their speed, slowing the transistor. But by increasing the density of electrons in the gate electrode, the oscillations can be avoided. By using a metallic gate rather than a polysilicon gate, we can conduct more electrons than the former, up to a scale of a couple of hundred. After finding a proper metallic gate with an acceptable work function, we can introduce high Kappa metal gate transistors. Another way for high Kappa dielectrics to improve CMOS transistors is by using a gate all-around FET structure. A structure like this will be able to extend the SI channel to less than 10 nanometer node, while continuing to allow the use of high Kappa gate dielectrics of modern times. It uses a silicon nanowire as a channel to the MOSFET channel, and has the metallic gate and dielectrics inside it wrapped by the wire. With atomic layer deposition and proper metal gate work functions, the MOSFET can be made. Unfortunately, this only solves the effective oxide thickness problem momentarily. For DRAMs, we need a way to minimize effective oxide thicknesses, or EOT values, and have a small leakage current. Metal insulator metal capacitors, or MIM caps with metal of high work functions, are being researched. The main problem with this is that for these MIM caps to work, they must be compatible with the high aspect ratios that now exist in modern DRAM capacitors. By using atomic layer deposition, this problem may not linger in a few years. EOT values have to be very minimal also, at around half a nanometer to 0.35 nanometers, with leakage current no less than 100 nanoamps per centimeter squared at 1 volt. With these conditions, the promising dielectrics mentioned before change when trying to achieve these high aspect ratios, decreasing their constants. And with incredibly small EOT values, optimizing electrodes and dielectric/electrode interfaces are very important to maximize the EOTs. With a metal with a high work function, this problem will be solved, if not for the complexity of finding the right metals suitable. As of today, one of the dielectric films with the most promise to these problems is strontium titanate, or SRTiO3. As research proves, it can have a leakage current as low as 100 nanoamps per centimeter squared at 1 volt. The behavior of the crystals of the SRTiO3 has also been researched using S-ray powder diffraction. The crystallization temperature becomes raised as the composition changes from the stoichiometric structure of SRTiO3, but the temperature still stays below 600 degrees Celsius. Electrically, SRTiO3 films change greatly, as the deposited films and films with a 500 degrees Celsius anneals end up with a dielectric constant of around 20. This leads to an amorphous SRTiO3. Films with an anneal of 550 degrees Celsius and higher became crystallized into a structure with a dielectric constant of approximately 150. When compared to EOT versus thickness plots, the values of the dielectric constant correspond to the slope of the graph. Research is being heavily invested in applications of high Kappa dielectrics for non-volatile memory, for example resistive RAM. The market for NAND flash memory has grown very successfully because of its density integration potential, making it easy to manufacture larger arrays of memory. Today, flash memory uses floating gate architectures. Each word is usually made using N+ polycrystalline, which go over multiple floating gates. Silicon oxide, nitrogen oxide are used in stacks between the storage floating gate and the top control gate as inter-polysilicon dielectrics. Currently, the polysilicon will wrap itself around the floating gate, where the sidewall overlap adds to the capacitance that is sandwiched between the top control gate and the floating gate, giving the critical coupling to have the device work. With outside voltages through the top control gate, it creates a voltage drop over the dielectric between the floating gate and the silicon substrate, creating carrier transports through the tunnel the dielectric lays in, or the minimal amount of bias to read the charge stored in the floating gate. When the size becomes smaller, less than 40 nanometers, the floating gate architecture must be modified because the physical space between the cells become too close and do not let the control gate cover the floating gate. When modified, the structure created will look as a single place, and the coupling capacitance will be lost. When this happens, the sidewalls leads start to break down and lose its coupling factor. A solution to this are high kappa dielectrics. Research today is trying to switch out the stacks of ONO as interpolysilicon to create larger coupling factors in the gate. Semiconductors with large band gaps are very useful for future power devices. For the past 20 years, huge improvements have been made to the doping, processing, and growth of high-power devices. The problem with this is that unlike its theoretical results, the breakdown voltage is always smaller than the estimated because the structure of the semiconductor used is not uniform, and with crowding of the electric field at the corner of the electrode. When using high-power technology, the breakdown voltage of the dielectric might be visible before the semiconductor is used. By using high kappa dielectrics, we can decrease both the electric field inside the oxide and chance of premature breakdown of the dielectric. As the relative permittivity of the dielectric grows, the electric field in the oxide falls, and as a result raises the breakdown voltage of the diodes. The ratio of the experimental breakdown voltage and the theoretically ideal breakdown voltage, called the termination efficiency, jumps at a large rate for bigger values of relative permittivities, independent of the angle ramp. High kappa dielectrics are the future for the next generation of capacitors, transistors, and diodes. The increase in the dielectric constant will surely help Moore's law stay true for years to come. Today, our most promising dielectric is hafnium oxide, where it is already being used in CMOS transistors, breaking performance records. With DRAM and flash, more memory can be stored with dielectrics. As more and more research is placed into high kappa dielectrics, future technology will become boundless. These are some references if you want to find out more about high kappa dielectrics, and thank you for watching my video.